Okay. So, we now move to the next topic, again a very basic topic, and I believe you must have studied it somewhere, but then it is better to again take a relook into this. This is Z transform. We start with DTFT. That is given x n, it has a DTFT capital X e to the power j omega, which was x n e to the power minus j omega n, n from minus infinity to infinity. And these are infinite sum. So, its magnitude is a complex sum of course, because e to the power minus j omega n is complex. So, magnitude of the overall summation may converge, this may be finite or may not converge. If it does not converge, I said this DTFT does not exist. So, for that we had earlier derived one necessary and one sufficient condition, that is for this to be finite, for this to hold good, it is sufficient to have that is x n should be such that mod value, absolute value should be, I mean if you take a sum, it should be summable, that is the sum should be finite. If that happens, DTFT will always exist. This is a strong condition, sufficient condition. If it happens, DTFT will always exist, but it does not mean that if it does not happen, DTFT will not exist, it may or may not, but this is a safety case, that if it happens, DTFT will exist. That is what we studied there, right. Now, here you see, consider the term e to the power j omega, right. So, this sum, I can generalize, consider the complex plane, this is a complex plane, we call it Z plane. Okay. Z plane means every point has got, if it is Z, you can draw a line. So, and if this is theta and if this length is r, Z basically is r e to the power j theta. Here we will be interested in the polar form, not in rectangular form like a plus j b, but in this kind of polar form, that is not r, sorry, this is Z. Okay. Now, what is this? This is Z, okay, with r equal to 1 and theta equal to omega. So, e to the power j omega is a special case of Z, where the magnitude part is 1. Okay, so, this may be 1, this could be 1 and theta is the given omega. So, that means, depending on the omega you have, omega can be 0 and it can go up and then become 90, then 180 and like that, but magnitude will be always 1. Okay. Omega can be anything from 0 to 2 pi, okay, because this DTFT is periodic over a period 2 pi. So, you can take it from minus pi to pi. So, omega here the DTFT omega can be from, or equivalently omega can be from 0 to 2 pi or 0 to 2 pi also. Total period length should be 2 pi. So, minus pi to pi normally we take this, it could be 0 to 2 pi, you can view it that way also, we normally take this. So, omega in this equation will take value from minus pi, that is from this minus pi, this much, and then it will become less negative, it will go in this direction and will become plus pi. Okay. So, omega can vary from minus 180, then less, minus 90, then less, 0, then again positive to 90 and then 180. So, it covers 360 degree, 2 pi, range of 2 pi in this, but magnitude remains always 1. So, that means, as omega changes in the Z plane, I am moving on a circle, we call it unit circle, okay, unit circle, because radius is 1, and then depending on where you have for the particular omega, suppose this theta is now omega, this much omega. So, this is your Z now, r is 1, this much is 1. So, you are here for that Z which is equal to the power j omega, you are running the summation. So, for a general z in this plane, that is if I come out of the unit circle and go here, here, anywhere, for a general z, a more general sum would be like this. Where z is sum r and sum e to the power j omega. Okay. And this is a general sum, I call it x z, provided the sum, even though it is infinite sum. So, it may exist, may not exist, its mod may be finite, may not be finite. When I write this, I am assuming it is finite, exists. Then this summation is more general summation, and I call it z transform of x n. X z is called z transform of x n. Why it is more general? Because this in this summation z can take any value over this z plane, not necessarily on the unit circle, number 1. Number 2, if I restrict z to be on the unit circle, then magnitude of z is 1. So, z is just 1 into e to the power some j omega, that is e to the power j omega. If I put that back here, I get dTft. So, dTft becomes a special case of z transform, where either you write as z equal to e to the power j omega, or equivalently you write mod of z, which is magnitude, which is r 1. Okay. So, this is a more general summation, and it allows you the flexibility of choosing z from anywhere in the z plane. This has a tremendous advantage, we will see later, because it will give rise to the concept of poles and zeros, which can be anywhere in the z plane and not necessarily on the unit circle. So, that is why you have to allow this variable to go out of unit circle, make it be a more general variable z, whose special case will be this e to the power j omega for mod z, that is r equal to 1. Okay. So, I am allowing now the complex variable to go out of unit circle. If it were in a unit circle, it would have been e to the power j omega. Now, I am making it general. So, it is not restricted to be on the unit circle, it can be anywhere on this complex plane. Typically, of the form z is r e to the power j omega, r is the magnitude, omega is the angle, and then this summation becomes a more general summation. I call it z transform, a capital X z. Its special case is dTft, when z is e to the power j omega, magnitude 1, that is I am on the unit circle, angle omega. Then the z transform turns out to be nothing but dTft at omega, because if you replace z by this, you get nothing but dTft formula. I am assuming this exists. This summation, this has some also additional advantage, that suppose x n is such, that this should have been less than infinity, which is a sufficient condition for dTft to exist. But suppose it is not less than infinity, it is going to infinity. Then if it goes to infinity, dTft may exist, may not exist. We are considering the case where it does not exist. Okay. If it is less than infinity, it will always exist, but if it is going to infinity, it may or may not. I am considering the case where it does not exist. But if instead of dTft, we go for z transform, then for proper choice of r, magnitude of r is what? Mod z, because z was r e to the power j omega. So, for proper choice of r, magnitude of z, we can still have the z transform converging, okay, existing. What? As an example, consider x n to be say 2 to the power n u n. So, it is like this, x n is 2 to the power 0, that is 1, then 2 to the power 1 2, 2 to the power 2 4, dot 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 dot, all positive, and this side is 0, because you are multiplying it by u n. Okay. U n is 1 on this side and 0 on this side. So, 2 to the power 0 into 1, 2 to the power 1 into 1, 2 to the power 2 into 1. So, you get those values and 0 on this side. This sequence, for this sequence, this holds, because you see all values are positive. So, mod of x 0 1, then mod of x 2 2, then mod of x 1 is 2, mod of x 2 is 4, and dot 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 dot. This summation, you can understand that it goes to infinity, which is increasing 1, 2, 4, then 8, then 16 is going on. Okay. It is a GP series, but as it goes to infinity, it will go to infinity. Okay. So, this is not absolutely summable. So, for this DTFT actually does not exist, but if I take the Z transform you see x n z to the power minus n, here n can start from 0 because values to the left hand side for x n are 0. So, 0 times z to the power minus n, it makes no sense, because 0 times this is 0. So, I do not consider them. I start from n equal to 0 and go on to infinity, because for n less than 0 the sequence x n has values 0. So, product is 0. So, no point in considering them. Okay. So, this means 1 into, you see this summation at z you write as r e to the power j omega, all right. This summation, its mod value, okay, as before, it will be less than equal to, as I told you last time, summation of mod by the triangle inequality is less than equal to, mod of a summation, okay, mod of a summation by using the triangle inequality again, mod of a summation is less than equal to summation of the mods, okay, and mod will come here, mod of a product, mod will come on this x n into z to the power minus n, but there is a product of two terms, mod of a product is product of mods. So, this into mod of z to the power minus n, z is r e to the power j omega. So, r to the power minus n e to the power minus j omega n. Again mod of a product is product of mod, but mod of e to the power minus j omega n, this is equal to 1. Any e to the power j theta has magnitude 1. So, 1. So, you are left with r is a positive number, r is the magnitude. So, r to the power minus n still a positive number. So, mod has, there is no point in taking mod, because mod of a positive number is the number itself. So, r to the power minus n. Now, what is mod x n? X n itself is 2 to the power n u n. Okay. I will now consider, because u n is present, I will start from 0 to infinity, and then 2 to the power n all positive numbers, that is 2 to the power 0 1, 2 to the power 2 4, 2 to the power 3 positive numbers. So, no point in taking mod. You can just take 2 to the power n only, and I am considering from 0 to infinity. I am not considering negative terms. So, u n, presence of u n is taken into account. So, this summation is actually 2 by r whole to the power n. You see, if I take r greater than 2, that is, if I in the complex plane, if you draw a circle of radius 2, and if I am here, anywhere where mod, suppose this is z, this much is mod z, is greater than 2. If I choose z here, 2 by r, because r will now be this much, r is greater than 2. So, 2 by r less than 1. So, less than 1, as it gets powered up, it becomes lesser and lesser. Less than 1, suppose it is half. So, half to the power 0 1, okay, half to the power 1 half, half to the power 2 1 by 4, half to the power 3 1 by 8 dot dot dot. So, it will be a decaying thing, and the summation will exist. You understand? For instance, that is what I am saying. Suppose r is 4. So, we will have half to the power 0, that is 1, then half to the power 1 half, then half to the power 2 1 by 4, 1 by 8 dot 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 dot. This summation will exist. We all know 1 plus x square plus x cube dot 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 dot, it exists and is given by 1 minus x. If mod x is less than 1, mod x is half, that is less than 1, so they exist. So, that means, in this case z transform will exist, the mod value will exist, because this is finite. So, because I am allowing the complex variable to go anywhere, I can choose z anywhere in this z plane. In this case, I take z to be such that its mod value, that is magnitude, is greater than 2, and therefore, the summation exists. So, this is an advantage, that even if DTFT does not exist, by clever choice of the magnitude of z, that is r, you can still have the z transform exists. Okay. This is another motivation, but I tell you, main motivation is that you are now free, you are from the unit circle, you can be anywhere in the z plane. So, you get a more general expression, and this will give rise to something called pole and 0, which we will consider later, and that will be related to stability causality. Okay. That is the main reason of this generalization. Now, we talk about the convergence issues, in fact, we call regions of convergence. Before that, consider x z. mod x z is repetition, mod of this, mod of a summation is less than equal to summation of mod, is just repetition of what I just told, and mod of a product is product of mods into mod of z to the power minus n. From that I will get only r to the power minus n like before, because z is z to the power minus n is r to the power minus n e to the power minus j omega n. Mod of this is mod of this into mod of this, but mod of this is 1, and r to the power minus n is always positive, r is positive number. So, any power of r, positive, negative, whatever, that will be positive. So, mod of a positive number is the number itself, that is why I do not put a mod here. Okay. This is in general true. Okay. Now, suppose this x z, mod x z exists, suppose this exists, that is it is finite for some z with r into the power j omega. Okay. Then that means, if you draw a circle in the z plane of radius r, omega has no effect on this summation. If it is exists, that is, if it is finite, suppose this is finite, this is finite, suppose this is finite, and therefore, this exists. It is finite for some z whose magnitude is r into e to the power j omega. Now, you see this summation has got nothing to do with omega, it is free of omega. Okay. So, therefore, if I draw a circle of radius r, at any point on this circle we will have the same magnitude r, omega will vary, but since this summation does not depend on omega, therefore, whether I am here, whether my z is here or here, whatever z I put, for all of them the same r will come here, and if it is less than infinity, that is, if it is finite for any r, any z, it will be finite for any other z, because their r value is same. So, that means, this summation, if it exists for any z, then you draw a circle through that z, taking the magnitude of that z as radius, that is r as radius. Then on the whole circle, full circle, any point if you move to, from z to z prime to z double prime, anywhere, at every point this summation will be finite, and therefore, z transform will exist, because at every point mod z or mod z prime or mod z double prime, there will be r. Okay. And if it is, we have already seen that since z transform I am saying it is existing, that is, this is finite for one z for which this is r. So, that means this summation is finite. So, if I move to z prime, z double prime, anywhere on this circle, radius is still r, magnitude is still r, and that is, if I have x z prime, for that also, if I have z prime, suppose x z prime, if I have z prime to the power minus n, it will eventually be less than equal to the same thing, because difference between z and z prime is in terms of the omega, this much omega here, this much omega here, r is same, and this summation is independent of omega. So, whether you have z here, z prime here, z double prime here, whatever, there is z prime here, z double prime here, z here, this will always be less than equal to this, and this is free of omega. Okay, this is free of omega. So, if it is finite, it is finite for any z, z prime, z double prime, because it is r everywhere, same r. Okay. Therefore, it means that if z transform exists for a particular z, then if you draw a circle through that z of the same, of the radius of what radius? Mod of that z, which is r. Then for any z, any on this circle, this summation still will be, this mod of x z for any z on this circle will be finite. Okay, therefore, it will exist. But there is a little more than that. If this is finite for some r is the radius of the circle, then it cannot be, it cannot go to infinity immediately if I increase, if I go from r to higher side, r plus or r to r minus. That is, because of the continuity, if it is finite, if this summation is finite for some r, this much r, the real axis, okay, this much r, then it is not possible that immediately to the right of R, immediately to the left of R, this summation will go shoot up to infinity. It is not possible. There will be a band because of the continuity, however small that band. Okay. Within that, the summation will still be finite. It cannot be arbitrarily just for a point. Okay. If that be, that means, I mean, if I draw a circle of this much radius, or of this much radius, or of this much radius, okay, for all of them, I will get things like this. That is, suppose this part is R1, this part is R2. So, I draw one circle of radius R1, draw another circle of radius R2. So, since this band, there is this will be finite for R taking not only one value here from R1 to R2, this entire band R can take R1 greater than R1, still greater than R1 up to R2. For this entire band, okay, this summation will be finite. It can be finite just for a specific R, and then all R to the right, all values to the right, all values to the immediate left, immediate right, it is shooting up to infinity. That cannot happen because of the continuity of the thing. Therefore, at least there is, however small, however narrow, there will be a band around R, that R. So, this band may be from R1 to R2. So, from R1 to R2, any value you can give to R, this summation will be finite. And therefore, if I draw one circle with radius R1, another with R2, then the entire region will be my part of region of convergence, because if I pick Z from here, this much radius, this is between R1 and R2. So, R, there is a magnitude of Z will be between R1 and R2, it will fall in the band, and if I am falling in the band, for that R the summation is finite. So, DTFT will exist, which means we will have this annular ring, this ring which is shaded here, and I will call it region of convergence. Sometimes R1 can shrink to 0. So, it will be whole inside of a circle. Sometimes R2 can go to infinity, that means the outside circle goes up to infinity. So, it is outside a smaller circle of radius R1. Sometimes there can be multiple rings, okay. But this is a typical shape of region of convergence. Okay. That within this region, if you pick up Z from anywhere, this Z transform will exist. This is called region of convergence. With that in mind, let us consider various sequences, finite length, right sided, left sided, etc., etc. Okay. So, consider one sequence, say in general, say from finite duration, and I am starting from right hand side going up to right hand side, n1 to n2 to start with, that is n1 less than n2 greater than 0. If the sequence is over this range, outside this range it is all 0 values, this is my x n. So, in this case Z transform, no need to consider the summation from minus infinity to infinity, we have to start from n1 to n2 x n z to the power minus n. So, mod of x z will be this as before, summation of mod less than equal to mod of summation mod of summation less than equal to summation of mods, mod of x and mod of a product is mod of x n, and from here r to the power minus n will come. So, we have done. Now, you see this is not an infinite sum, this is a finite sum, all right, this is a finite sum, and this finite sum will always exist. Only if you take r equal to 0, then there is a problem, because 0 to the power, you see n, small n is taking value from capital N1, which is positive, then further positive, further positive, further positive up to n2. So, there are negative powers of r. So, if you take r equal to 0, then this summation will not converge, but otherwise it will converge always, okay, for any r. That is, in this case the entire z plane, that is, you can take any z of any r and move a circle around that of that r, okay, all points on that circle with the same r, okay, and this summation will be say finite summation, it will exist for any r you choose. You can move the circle, you can expand r, contract r, only thing is origin cannot be included. If you have got negative powers of r. On the other hand, if you have got the summation localized here n1 n2 and n1 less than n2 less than 0. In this case, n1 negative, n2 negative. So, there will be positive powers of r. Okay. But even then this is a finite sum. So, this will be finite. Only thing you cannot take r going to infinity. If r is taken as infinity, the summation will be infinity. So, in this case, origin is allowed in the z plane, origin is allowed, but infinity is not allowed. And if you have got a situation like this, n1 on this side, n2 on this side, then in this summation you will have both negative powers of n, positive powers of n. So, both origin and infinity will not be allowed. All right. So, that means here ROC means entire z plane except origin if n2 is positive, because n2 is n1 can be negative, but if n2 is positive there are some negative powers, because small n will be positive. So, minus n will be negative. So, there will be some negative powers of r, which means r equal to 0 will be ruled out. So, that means except origin if n2 is greater than 0, and in that case that is if n1 n2 both are on this side, r is r equal to infinity, no problem, because negative power infinity will be 0. So, that does not cause a problem. On the other hand, if you have got n1 n2 both on this side, they are negative. So, actually small n take negative value means minus of n take positive value. So, r to the power some positive number, here r equal to 0, origin no problem, but r equal to infinity is a problem. So, in one case ROC is the entire z plane except origin if n2 greater than 0 and except infinity if n1 less than 0 and both, that is except origin except infinity, both if n1 less than 0, n2 greater than 0. All right. This is ROC of a finite. Otherwise, this is a finite sum, it exists for any finite r, okay, any non-zero, non-infinity r, and therefore, Z transform exists. That is for a finite duration sequence. Thank you very much. In the next class, we go for the other sequences.